one possibility. So let's say we are given a function f of x equals, let's say 2 to x minus 1 plus 4. I have to identify that the base function is 2 to the x, and I will graph it on the side immediately. I know it's this. When the base is greater than 1, the function is increasing, so this is 2 to the x. Then I have the transformation x into x minus 1, which shifts the graph to the right one. So this point now moves here. So this second one is 2 to x minus 1. And now I have 2 to x minus 1 plus 4, which shifts the graph up 4 units. Now, I know that the horizontal asymptote is y equals 0 here. But when I graph the final graph, I have to shift the horizontal asymptote 4 up. 1, 2, 3, 4. This is the horizontal asymptote now. And this point, which was at 1, 1, of course, moves up here at 1, 5. So here's the graph. And this is 2 to x minus 1 plus 4. There are no x-intercepts, but there is a y-intercept. How do I determine the y-intercept? I plug in 0. 0 minus 1 is negative 1, which is 1/2 plus 4. 2 times 4 is 8, plus 1 is 9. So this point here is 0, 9/2. And there is nothing else that anyone can ask other than we know the domain is everything. Can anyone identify the range for us?
Would it be 4 to
Indeed, 4 to infinity. It cannot touch it because it's the horizontal asymptote. So it will be open parenthesis, open parenthesis, in other words, 4 to infinity. Very good. Now, this is for an exponential. What about a log? So let's say f of x equals natural log of x plus 2 minus 1. I know that the base function is natural log, which I know it's the opposite of that. I shouldn't say opposite, sorry. I should say the inverse, right? But what I meant to say is it's a reflection. That's what I meant to say. Base is e, so it's an increasing function on its domain. So then when I graph x plus 2, I have to shift the graph 2 units to the left. Now the vertical asymptote has to be moved first, because the vertical asymptote here is x equals 0. Now it's x equals negative 2. How do I know? Let's find the domain. X plus 2 greater than 0, x greater than negative 2. So the domain of this function is negative 2 to infinity. That's why the vertical asymptote is here. So now this point, which is 1, 0, moves 1, 2. 2 to the left. So here's the new graph. And this is natural log of x plus 2. Down 1, not a big deal. This point will move here at negative 1, negative 1. Too much on one graph, so I'm going to graph it here. So, of course, I have to graph x equals negative 2. And then move the graph here. I don't know where it crosses the x-axis and the y-axis. So this is natural log of x plus 2 and minus 1. Not a big deal. I can find the x and y intercepts algebraically. I already know how. So f of 0 is natural log 2 minus 1. And I have to approximate this because I don't know what that is. So with the calculator, natural log 2 minus 1. So negative 0.3. negative 0.31. So f of 0, so my graph is incorrect. So f of 0 should be here. So I will not correct anything there. That was my assessment initially, but I will correct it now here. So the y-intercept is a little below, tiny below the x-axis. So something like this. So I corrected my graph, natural log x plus 2 minus 1. And now I have to determine this. So I have to set the function equal to 0. So natural log of x plus 2 minus 1 equals 0. I move 1 to the other side. Natural log of x plus 2 equals 1. So e to the first power equals this. E to the first power equals x plus 2. So this is equivalent to e to the first power equals x plus 2. So x equals e minus 2. Again, I have to approximate. I don't know what this is. Roughly 1 point something. So we can put in the calculator. So this is e. Here it is e minus 1. I'm sorry, y minus 1 when it's minus 2. Okay, so it's 0.72. So I determine this point, 0.72 comma 0. Everything is based on what we did together in this chapter. So something very simple, nothing sophisticated about an exponential or a log. Very simple. Nothing that will take you more than 3 minutes. What do you need help with? What would you like to continue with?
Can we go over condensing?
Yes. Do you have a problem for us?
No, I didn't have a specific one.
Okay. So let's choose then. So let's do condensing. Condensing. We can go back to that particular section, or we can go back to the review. So these are examples of condensing. I think we did all these. So condensing right here. So they're in section 5.3. You want to choose from here, or I can make...
Yeah, we do 56.
56, very good. Or I can make one up, no problem. Good. So first we have to address the numbers in front. That's very important. So this is log x to the third plus natural log y to power 4. Then I can address the summation, the sum here. So natural log of x cubed y to the 4. So basically there are only 3 properties. The power that goes in front and also comes back, the sum that is a product, and the difference that will be a ratio. Only 3 properties. Is this okay?
Yes, thank you.
Perfect. What do you want us to continue with? Anybody? Everybody? Do we need to review any further? Yes, no? So are we continuing our review or everything is clear?
Can we do a word problem?
Yes, from exponential growth, exponential decay, logistic growth model.
Can we do one of each if that's possible?
Sure, absolutely. Okay. So here's the exponential growth. The function given to us models e-commerce sales in the United States in billions of dollars years after 2002. So let's read on and see if this is what we want. Use the exponential function to round to the nearest billion, and it says to find the sales in 2012. Use the exponential function to project the year rounded to the nearest. Okay. So they're giving us a graph. And they're asking us these questions. Let's see if there is a part C. No, there is no part C. So that's one option. This is the exponential, this is the logistics growth model, which we already did last time. If you want, we can choose another problem. I think we also did the Hispanic population. I think we did the exponential decay. Do you have a function for us from, or a problem for us from your homework that you want to look at? So this is the exponential growth, this is the exponential decay, and this is the logistic growth model. So we just found 3 more. And also this one, population of Germany.
Can we do 29?
Yes, let's do 29. Perfect. And we have f of t equals 140 divided by 1 plus 9e to negative 0.165t. Describes the population of an endangered species of elk T years after they were introduced to a non-threatening habitat. Okay. Now, how many elk were initially introduced to the habitat? So initially, how many were introduced to the habitat? What am I asked to find? What are we at? Yes? Say it again.
Will we find T?
So how many elk were introduced initially?
40?
Say it again.
140?
What do we need to do? We cannot guess. What do we need? Let's think of, first of all, what we need to do. How many were introduced initially? And we talked about initially, originally, at the beginning. What does that mean? When we talk about initially, originally, at the beginning, what do we refer to?
Would this be like t equals 0?
Perfect. So we have to find f of 0. So 0, e to 0 is 1. 1 plus 9 is 10. 140 divided by 10 is 14 elk. Part B. How many elk were expected or are expected in the habitat after 10 years? What are we asked to determine now?
Would we plug in 14 now?
You mean 10? After 10 years. Does it say 14? How many elk are expected in the habitat after 10 years? Okay, so we'll plug it in the graphing calculator. So we have 140. Be very careful how you enter it. So I recommend putting it in y equals. That's the safest place. 140 divided by, in parentheses, 1 plus 9 times e to negative 0, so it's 0.165 t. Close the parenthesis for the power, come down and close the parenthesis for the denominator. And now, obviously, when I plug in 0, just for the sake of the argument, I see I get 14. And when I plug in 10 years, I see I get 51. I cannot round elk. Good, 51. So now let's see what they want. What is the limiting size of the elk population that the habitat will sustain? Which means as time goes by. So 10 years, let's try 50 years. Let's try 100 years. Let's try 200 years. Obviously, the limiting size is the numerator in this case. So as t goes to infinity, which is not really possible, as t goes to infinity, f of t gets closer and closer to 140. How do I know? I checked. I increased the time as much as I could. And the result was always 140 elk. Any questions? Is this okay? Okay, good. Let's go back. So that's what this was, the logistic growth model. So this is the exponential growth or decay, because I see it has a negative coefficient here, a negative growth rate. Annual growth rate is negative, so this is not increasing, this is decreasing. Then we have an exponential decay model here. If you want more word problems. So what do we continue with? Now we have here exponential and log equations. Again, we have condensing, we have expanding. What would you like to continue with, please?
Can we do 28?
Yes. So let's look at 28. Good. So 28. Use the exponential decay model. Yes, we know. This is it. A of t equals a0 e to kt. Yeah. To solve this exercise, the half-life of iodine 131 is 7.2 days. So the half-life is 7.2 days. Good. Let's read on. How long will it take for a sample of this substance to decay to 30% of its original amount? And then it says round to 1 decimal place. Fine. Okay. So remember the half-life, you can use the direct formula, which is fine, or you can simply go through the steps. So if you want to go through the steps, it means that when time is 7.2 days, A of 7.2 days is the original divided by 2. This is the point. So when we are given that the half-life is 7.2 days in this case, we know that this original amount becomes half after 7.2 days. So the point is 7.2 A0 over 2. I plug the point in. How do I do this? So A0 divided by 2 equals A0. E to time is 7.2 times K. Of course, I will simplify. That's the whole purpose. I have here 0.5 equals, and I apply natural log, 7.2K, so K equals natural log 0.2 over the half-life, which is 7.2. So, of course, I haven't finished, but what I'm saying is you either memorize or write it down, natural log of 0.5, which is 1/2, natural log of 0.5 divided by the half-life. That will be your decay rate. Or you go through the steps, you don't have to memorize anything, as long as you understand that the half-life gives us this point. Then you can always develop it in 30 seconds. If not, you can just use the formula. So now I will have to divide natural log 0.5 divided by 7.2 to see what is K. And for K, I highly recommend always for the growth rate or decay rate, always use 4 decimal digits. It's an exponential function, and a tiny difference means a lot of error. So I have natural log of 0.5, and I divide by 7.2. So I got, as expected, a negative number. So then K equals negative 0.0963. So I highly recommend 4 decimal digits. So now I have the model. So the model is A of t equals whatever original, e to this number times t. And now I can address the question. How long it takes for the original to decrease to 30% of that amount. We had these problems last time also. So 0.3 A0 equals A0 e to this. And of course, the original amount doesn't matter. The way the problem is set up, I apply natural log to both sides, and then I find t. So remember, in 7.2 days, it drops to 50%. So the answer has to be more than 7 days. Because in 7 days, it drops to 50%. It needs more to drop to 30%. So it must be more than 7.2 days. So we apply natural log to both sides, of course, and here, negative 0.0963t. So then t equals natural log 0.3 over this. Make sure you do not get a negative number for time. Okay, so we have natural log 0.3 divided by, the best thing to do is, if you still have this number in there, divide by parentheses the previous answer. You will get the best answer possible. So 12.5. So time is 12.5 days. As expected, it has to be more than 7. Because in 7 days, it drops to 50%. In 12 days, it will drop to 30% of the original amount. which makes sense.